Take a look at this water bottle. Nothing special happens when we squeeze it, right? The water inside stays the same. Under great weight, the bottle may deform significantly, but the water inside remains water, just as liquid and fluid with the same density. Now, what if we take a harder object, a piece of iron, and try to compress it with our hands? There'll be no visible changes. Of course, under extreme weight, it might change shape. But metal will remain metal, it won't become liquid or brittle. But what would happen if we applied the same extreme pressure to these materials? We bet you'll be surprised. In this video, you'll learn, can hydrogen gas turn into metal? What really destroyed the submersible Titan? Where underground is there enough water to submerge our entire planet under a kilometer of liquid? Where does it constantly rain diamonds? You'll learn all of this and much more in today's video. Extreme pressure. Don't forget to like and subscribe to our channel for more interesting content. Now let's set out on a journey to the center of the Earth, and we'll start from afar by exploring the pressure in our planet's orbit, in the atmosphere. Then we'll descend to the surface and eventually reach our planet's core. Along the way, we'll find out what happens to gas, water, iron, and other substances under different pressures. But let's start by defining what we mean by pressure. In short, it's the force applied over a unit area of a surface. The concept can be illustrated with a simple example using your smartphone. Imagine placing an iron cube the size of your phone's short side on the screen. The cube presses on the area of the screen beneath it. The pressure is equal to the weight of the cube divided by the area it presses on. And the screen doesn't budge. It can easily handle that pressure. Now let's place the same cube on the screen, but this time on its corner. Don't try this at home. The screen will almost certainly crack. What happened? It's the same cube and it hasn't gotten any heavier. That's right, the weight is the same, but the area that the weight presses on has become much smaller. As a result, the pressure increased significantly. Our ancestors noticed this pattern. They realized that it's much easier to pierce an animal's hide with a sharpened stick and eventually inverted the spear. Then around 3,500 years ago, in the Bronze Age, people sharpened a metal rod to create the nail, an invention we still use today. Isn't it fascinating? People didn't yet know what pressure was, couldn't measure it, but already knew how to increase it. Oh, and by the way, how do we measure pressure and what units do we use? Not just one, but several units of measurement have been adopted. Since we'll be working on a planetary scale in this video, we'll use atmospheres as the most convenient and illustrative unit. Let's first clarify what that means. In case you didn't know, all that air above your head reaching all the way up to space isn't weightless. Even Aristotle understood that air has weight. If you use the humid air from your breath to inflate a balloon and let it go, it will fall to the floor. But if you fill it with helium from a tank, it'll float to the ceiling because helium is lighter than air. So the pressure on Earth at sea level is considered to be 1 atmosphere. Now let's clarify what 1 atmosphere means. Is it a lot or is it a little? It's equivalent to having a large horse step on your foot, or a hefty cow. This isn't a joke. When on all fours, an animal weighing 500 to 600 kilos, that's 1,100 to 1,300 pounds, exerts approximately the same pressure per leg on the ground. So why don't we constantly feel the weight of a horse in the form of atmospheric pressure? That's because our internal organs, blood and tissues, exert the same amount of pressure outward, balancing the external pressure. And here are a few more examples to put this into perspective. The pressure in your car tires is about 2 atmospheres. Garden sprinklers water lawns at 2 to 4 atmospheres. An espresso machine brews coffee at 8 to 10 atmospheres in the brewing chamber. And the water pressure at a car wash can reach over 100 atmospheres. We've sorted out air pressure, but what about water? The same principles apply. The deeper you dive, the stronger the pressure gets, because water too has weight. And the deeper you go, the more water mass is above you. Starting from a certain depth, you'll need a bathyscaphe, otherwise you will be crushed. Now that we understand the idea of pressure in general, let's take an exciting journey through the scale of extreme pressure. We'll bring along 100 grams, 3.5 ounces of water, 10 grams, 0.35 ounces of iron, and 1 gram, 0.03 ounces of hydrogen, and observe how they change under various pressures. Shall we begin? Exosphere, 1,000 kilometers, 621 miles above the Earth. The pressure is 10 to the negative 13th power. Yes, we're starting our journey in space. The pressure here is 10 trillion times less than normal atmospheric pressure at the surface of the Earth. There's virtually none here, a near-perfect cosmic vacuum. So what happens to matter under such extreme conditions? Actually, for the most part, nothing unusual. Metal remains metal with all its properties, plastic remains plastic, and glass remains glass. They can stay here for millions of years without the slightest change. So nothing will happen to our piece of iron here. But what about water and hydrogen? Oh, that's where things get interesting. We carry water in a container and hydrogen in a balloon. 1 gram, 0.03 ounces of hydrogen is enough to inflate a small balloon. In a vacuum with almost no external pressure, hydrogen remains a gas, but the balloon will expand because the pressure inside is higher than outside. It will eventually swell and might even burst. If we release hydrogen at this altitude, it will simply spread out, forming a small hydrogen cloud that gradually dissipates, becoming less dense over time. A completely different thing will happen with water. If we release water from the container directly into space, it will begin to boil, evaporate, and freeze, all at the same time. At regular pressure, it's impossible to see all these three processes at once. This happens because water turns from a liquid into gas under low pressure, then quickly releases heat into empty space, which leads to freezing. The liquid form of water as we know it only exists because of atmospheric pressure. The lower the pressure, the more water wants to break free and evaporate. And that's why water boils at 100 degrees Celsius, 212 degrees Fahrenheit at sea level, but at only 69 degrees Celsius and 156 degrees Fahrenheit on Mount Everest. Under no pressure conditions, water evaporates extremely quickly without any heating. Now imagine if our water were in a regular bottle in cosmic weightlessness. We'd witness an incredible sight. If you just slightly opened up the cap, the water vapor would burst out with force, rushing through the neck and propelling the bottle forward like a jet. How long would a human survive in such conditions? The answer is not promising. Mere seconds. At such a low pressure, blood would boil instantly, causing us to lose consciousness before we would freeze or suffocate. Let's continue our journey along the pressure scale. The upper boundary of the mesosphere, 100 kilometers, 62 miles above the Earth. The pressure is approximately 3 times 10 to the negative 7th power. This is the nominal boundary where outer space begins. Here the pressure is 10 million times lower than at Earth's surface, yet still significantly higher than in the deep cosmic vacuum. What happens to familiar materials under such pressure? Almost exactly the same as in our previous location. Although much greater, the pressure remains extremely low. Our piece of metal won't change at all. The hydrogen balloons, however, will expand to enormous proportions and may also burst. If the hydrogen is released, it will disperse in all directions, gradually losing density. Liquids face the same challenges here as they do at an altitude of 1,000 kilometers, 621 miles. Water cannot exist as a liquid under this pressure. At such low pressure, water cannot remain liquid. It either instantly boils, turning into vapor, or freezes, turning into ice. This means that ice is the natural state of water at this altitude. If you heat it, it won't melt in the usual way, Instead, it will go directly from solid to vapor without passing through a liquid stage. This process is known as sublimation. Searching for complex life forms at this altitude is a hopeless endeavour. We know that where there is no liquid water, there are no chances for the emergence of Earth-like life. Bacteria and spores accidentally carried to this height might withstand the pressure and temperature, but they would be immediately destroyed by radiation. In general, we have every reason to consider this zone practically sterile. Shall we continue our journey? Stratosphere, 30 kilometers, 18.6 miles above the Earth. The pressure is 0.01 atmospheres. There is some actual pressure here, although 0.01 atmosphere is minimal. It's enough to give air temperature practical significance. Our test materials behave differently here, but not all of them. The piece of iron remains unchanged. The hydrogen balloon, however, has shrunk. The gas has become slightly denser, but its properties haven't changed. It's still a gas. Water will also quickly begin to boil, turning into a cloud of ice crystals. But a noticeably larger volume of water will have time to freeze inside the container than at 100 kilometers, 62 miles. It will once again turn into liquid if heated above 0 degrees centigrade, 32 degrees Fahrenheit. This is a significant difference from the previous level. The water here could potentially sustain life. However, it is important to remember that at such low pressure, the oxygen needed for life dissolves in water much worse than at regular pressure. For example, even in a warm aquarium, fish wouldn't survive at this altitude. It's a strange paradox. The water is warm, fresh and clean, but impossible to breathe in. So let's continue our descent towards Earth and up the pressure scale. The pressure on Earth is 1 atmosphere. This is the zone of normal atmospheric pressure. Here everything as we know it, water flows, wind blows, and you can live without a spacesuit. The piece of metal, once again, does not change shape, nor does water. At 1 atmosphere, the abundance of life is striking. It's everywhere, in the air, in the water, on and below the Earth's surface. The properties of materials here are well understood. So let's move further along the pressure scale. From here, our journey will take us into the depths of our planet. We are approximately 6,370 kilometers, that's 3,959 miles away from the center of the Earth. Ready to dive into the ocean? 10 meters, 33 feet underwater, the pressure is approximately 2 atmospheres. Yep, just 10 meters down and the pressure has already doubled. In the ocean, the pressure increases by roughly 1 atmosphere every 10 meters, 33 feet. With each meter, the environment slowly but surely changes. However, this depth is not sufficient to alter the properties of the samples we brought with us. 40 meters, 131 feet underwater. The pressure is around 5 atmospheres. Here we'll see various marine life and recreational divers. For them, 40 meters, 131 feet is usually the maximum diving depth. But what about our samples? Metal remains metal, retaining its shape. The water also remains largely unchanged. However, a hydrogen-filled balloon will compress to nearly half its original size. If it had a diameter of 30 centimeters, 12 inches on the surface, it would be just over 17 centimeters, 7 inches at this depth. Note that it doesn't deflate. Rather, the hydrogen inside becomes denser due to the pressure and loses volume. Let's dive even deeper. 1.2 kilometers, 0.7 miles underwater. The pressure is about 121 atmospheres. Here we encounter deep sea marine life. In particular, we'll see the famous blobfish. Its body consists of a gelatinous mass without scales. It lacks a swim bladder which could easily collapse under such pressure. This fish is perfectly adapted to its environment. 2 kilometers, 1.25 miles underwater. The pressure is 201 atmospheres. At this depth, we'll find sperm whales. Their ribs are connected to the spine by flexible cartilage, which allows their rib cage to compress rather than break under high pressure. And now we're descending even further. 3.5 kilometers, 2.2 miles underwater. The pressure is around 380 atmospheres. The Titan submersible tragedy likely occurred here at a depth of 3.8 kilometers, 2.3 miles, when it was moving toward the Titanic wreck. The submersible was used for commercial dives to the Titanic's remains. The exact cause of the disaster remains unclear. However, the pressure of 380 atmospheres crushed the sub's hull. Essentially, it was an implosion. Everyone on board died instantly. They had no time to comprehend what was happening, as it takes our brain 150 milliseconds to process things, while water and debris took just 20 milliseconds to kill everyone. Let's go even deeper, to the very bottom of the Mariana Trench. 10.9 kilometers, 6.8 miles underwater. The pressure is 1,086 atmospheres. For those of us on land, this pressure is unimaginable. A person without reliable protection would be instantly crushed to death here. Exploring such depths requires the most durable and reliable technology. In fact, building the hull of a spacecraft is easier. Don't believe it? Let's compare the pressure differences that a spacecraft and a submersible must withstand. In space, the pressure inside the craft is just 1 atmosphere, while outside it's nearly 0. At a depth of nearly 11 kilometers, 6.8 miles, the pressure inside a submersible is still 1 atmosphere, but outside it's over 1,000 times greater. No spacecraft, not even those sent to Venus, could withstand such a pressure difference. You might think no life could exist at such depths, but this isn't the case. Various species of amazing deep-sea organisms live and reproduce here. So far, around 10 to 15 species have been identified at these extreme depths. These are complex organisms that live in total darkness at temperatures no higher than 4 degrees Celsius, 39 degrees Fahrenheit. Such depths have rendered photosynthesis impossible, but bacteria have adapted to metabolize hydrogen sulfide and hydrocarbons. The fact that life exists under such high pressure has significantly broadened our understanding of the physical limits of life. They're considerably wider than previously thought. But what would happen to our samples here? Hydrogen has become so dense that it has shrunk several times more in size. If our balloon had a diameter of 30 centimeters, 12 inches at the surface, it would compress tenfold to just 3 centimeters, 1.2 inches at the bottom of the trench. However, the balloon would suffer the same fate as the Titan submersible long before reaching the trench floor. No elastic material on Earth can withstand such extreme pressure differences. The same applies to our water container. From this point onward, we'll discuss the state of our samples as if they were in ideal containers capable of withstanding such immense pressures. So what about the water? Would its volume decrease under a pressure of 1,086 atmospheres? Surprisingly, no. Despite its fluidity and ability to change shape, water is practically incompressible. Even if you sealed water in a lead sphere and struck it with a sledgehammer, the water would seep through the invisible micro cracks in the lead, but wouldn't reduce in volume. Why is this? There's a lot of space between hydrogen molecules, allowing them to compress closer together. However, water molecules are already packed tightly, but because they're not constantly moving, water becomes fluid. As for the piece of metal, there's no doubt it remains as it was, whether in space or under immense ocean pressure. What would happen if we continued our journey deeper into the Earth? And generally, what would the pressure be at such depth beneath the Earth's surface rather than underwater? Would it be the same? No, it would be significantly greater, as rock is much heavier than water. This is obvious since rock and even sand quickly sink in water. Let's continue our journey, but this time within the Earth's crust. 11 kilometers, 6.8 miles underground. The pressure is approximately 3,000 atmospheres. The temperature is over 400 degrees Celsius, that's 752 degrees Fahrenheit. This is a blazing inferno. Let's see how our samples are doing. Hydrogen is compressed, but still in a gaseous state. Nothing special happens to it. However, water undergoes something extraordinary. One might assume that at a temperature 4 times higher than its boiling point, it should instantly vaporize. Yet the immense pressure changes everything. Under such conditions, water transitions into a supercritical fluid, a fascinating and bizarre phase where the substance possesses the properties of both liquid and a gas. Nothing much happens to our metal sample here. Its melting temperature will slightly increase and its electrical resistance will rise. But there'll be no visible changes, it won't even begin to glow red. There's no life at this depth, at least no living organisms were found in samples from the Kola Super Deep borehole. By the way, we have a detailed video about what was discovered in the Kola Super Deep borehole. Check the right corner for the link. Let's go even deeper, quickly covering kilometer after kilometer, mile after mile. At a depth of about 70 kilometers, 43 miles, we'll have passed through the Earth's crust and entered the upper mantle, the main layer of the Earth, which makes up about 84% of its volume. This layer extends down to about 2,900 kilometers, 1,800 miles. The pressure in this layer continues to rise at an alarming rate. Let's go further down the mantle. 200 kilometers, 124 miles underground, the pressure is up to 70,000 atmospheres. The temperature is up to 1,500 degrees Celsius, 2,700 degrees Fahrenheit. So what happens to our samples here? Practically nothing. Iron remains iron and won't even melt, as the temperature at this depth ranges between 1,200 and 1,500 degrees Celsius, 2,200 and 2,700 degrees Fahrenheit. Iron melts at 1,538 degrees Celsius under normal atmospheric pressure. But it will definitely glow bright red or orange. Water remains in its supercritical fluid state. Hydrogen compresses further but stays in a gaseous form. The extreme temperature prevents it from becoming a liquid. What's more fascinating at this depth is not our samples, but the environment itself. Here you'll find exotic minerals like olivines, proxenes and garnets. As pressure increases, atoms abruptly rearrange at a certain point, forming a new type of crystal lattice. The chemical composition remains the same, but the mineral itself transforms completely. The most common example of this is carbon turning into diamond. Are diamonds present here? Absolutely. This is precisely where they're formed. The process of diamond formation takes millions or even billions of years. Naturally, it's impossible to mine them at such depths. However, in volcanic regions, diamonds can be brought to the surface along with magma. As it solidifies, it forms kimberlite pipes with rich diamond deposits. Later, people transform these kimberlite pipes into giant cone-shaped quarries. Now let's go even deeper. 400 kilometers, 248 miles underground. The pressure is 140,000 atmospheres. The temperature is up to 1,600 degrees Celsius, 2,900 degrees Fahrenheit. We're still in the upper mantle, however our iron sample remains almost unchanged from the previous level as the pressure prevents it from melting. It will simply glow even more brightly. Water shows little change as well, remaining in its supercritical state. Hydrogen too continues to exist as a gas. What's happening around us? In the upper layers of the mantle we saw olivines and garnets. Here, majorite, an exotic variety of garnet, is added to the mix. As depth and pressure increase, olivines gradually transform into another mineral, wadsleyite. This mineral is incredibly rare and looks as alien as its name suggests, resembling a spaceship fragment. Even deeper we'll find ringwoodite. It looks mesmerizing, especially when you consider where and how this mineral is formed. On the Earth's surface, ringwoodite remains quite rare, yet it is abundant within the mantle. And this abundance has an intriguing implication. Ringwoodite can hold water within its crystal structure, in fact up to 1.5% of its own mass. This hypothesis aligns well with seismological data. If it's correct, the ringwoodite layer in the mantle contains far more water than all the Earth's oceans combined. If this water were somehow released and made its way to the surface, it would cover the planet in a continuous 800-meter, 2,625-foot thick layer. Let's keep going deeper. 660 kilometers, 400 miles underground. The pressure is 240,000 atmospheres. The temperature is up to 1,800 degrees Celsius. That's 3,270 degrees Fahrenheit. At this depth, we enter the lower mantle. Iron remains solid, glowing even brighter now, becoming whitish. Hydrogen is highly compressed, but remains gaseous. Water continues to stay in its supercritical phase. What's happening around us? Something significant has occurred. There is no longer any ringwoodite or majorite. Under such extreme pressure, their crystal structures have transformed. We now find ourselves in the realm of magnesium perovskite with traces of aluminium and iron. This mineral, commonly known as bridgemanite, is one of the most abundant in the Earth's mantle, especially in the lower mantle. Bridgemanite comprises 2/3 of everything at this depth. The remaining third is primarily calcium perovskite, or calcium titanate, in roughly equal proportions. Let's explain something here, although you might find it startling. Bridgemanite dominates the lower mantle, which stretches from about 660 kilometers to 2,900 kilometers. That's 410 to 1,800 miles, right to the edge of the Earth's core. The lower mantle makes up over half of the Earth's volume, specifically about 55%. And since 70% of this layer is bridgemanite, it means roughly 40% of our planet is composed of a mineral that almost no one has ever seen in their lifetime due to its rarity. What an unusual paradox. But we're not stopping here. Let's go deeper to reach the pressure of 1,000,000 atmospheres and beyond. At a depth of 2,200 kilometers, that's 1,367 miles, we reach a pressure milestone of 1,000,000 atmospheres. The temperature here is up to 3,000 degrees Celsius, that's 5,430 degrees Fahrenheit. We are now in the lower part of the lower mantle. The environment remains largely the same, but this is an important pressure threshold for the samples we've been carrying. Let's see what's happened to them. In the past, scientists believed that under such conditions water would transform into an exotic state known as Ice 10. This form of ice exhibits metallic properties. It's 4 times denser than regular ice and efficiently conducts electricity. This happens because extreme pressure brings water molecules so close together that the oxygen atoms form a cubic lattice. Meanwhile, the hydrogen ions move freely, which makes it possible to carry electrical charge. However, recent research suggests that the intense heat, reaching up to 3,000 degrees Celsius, that's 5,430 degrees Fahrenheit at this depth, prevents water from forming Ice 10. Instead, it likely remains in its supercritical state. That said, the question isn't fully settled, and this remains a subject of scientific debate. What about our iron sample? It will change significantly. Iron will most likely undergo a phase transition from its standard crystalline structure to a denser form known as epsilon iron. In this form, iron is denser, more compact, and much more stable under extreme temperatures and pressures. And what about hydrogen? At this depth, hydrogen compresses to just a few millimeters in diameter. Heated to such an extent its atoms lose their electrons, transforming into plasma, a state of matter that behaves like an electrically conductive hot gas. As we continue downward, we finally reach the boundary between the Earth's mantle and its core, known as the Gutenberg discontinuity. 2,900 kilometers, that's 1,800 miles underground. The pressure is approximately 1.38 million atmospheres, and the temperature is up to 3,500 degrees Celsius, 6,330 degrees Fahrenheit. How intense is this pressure? Let's put it into perspective. Do you think the Statue of Liberty standing on one stiletto heel would exert such pressure on its pedestal? Well, not quite. In fact, you'd need to stack another 5.5 Statues of Liberty on top of the first one. Naturally, no pedestal could withstand such a load. At this depth, water and iron behave similarly to how they did at the previous level. But what about hydrogen? Now things get even more interesting here. The idea of ice having metallic properties already sounds surprising, but the transformation of gaseous hydrogen into metal seems almost downright alchemical, doesn't it? It was previously thought that hydrogen could become metallic at a pressure of 1.4 million atmospheres. However, modern research indicates that even higher pressure is required. At 1.4 million atmospheres, hydrogen might not transition into a metallic state, but could instead enter a supercritical phase. As previously discussed, this unique state occurs at extreme temperatures and pressures, where the substance exhibits properties of both liquid and gas. Alright, so what goes on around us at this depth? The dominant mineral of the lower mantle, bridgemanite, no longer withstands the pressure here, which causes another transformation. Its orthorhombic crystal lattice collapses, transforming into a denser layered structure. This new substance is known as post-perovskite. Post-perovskite forms the enigmatic D double prime layer, a zone up to 200 kilometers, 124 miles thick, at the boundary between the mantle and the core. This layer has puzzled scientists for years due to the two unusual anomalies. The first one is density jump. In some areas, density changes abruptly, as if there's an invisible boundary. The second one is wave speeds. Seismic waves passing through the layer travel at different speeds depending on their direction. Why is this strange? Imagine dropping a pebble into a calm lake and seeing the ripples move at varying speeds in different directions. For a long time this was a mystery, but the discovery of post-perovskite helped scientists understand these strange phenomena. Now let's continue our descent towards our ultimate destination. 3,100 kilometers, 1,926 miles underground. The pressure is approximately 1.5 million atmospheres. The temperature here is up to 4,200 degrees Celsius, 7,600 degrees Fahrenheit. We've entered the Earth's outer iron core. Under such conditions, iron is in a molten state. So the outer part of the core, which is about 2,250 kilometers, 1,398 miles thick, consists of very hot liquid metal. Now, let's go toward the very center of the planet. 6,371 kilometers, 3,958 miles, the center of the Earth. The pressure is up to 3.7 million atmospheres. The temperature is up to 6,000 degrees Celsius, 10,830 degrees Fahrenheit. We are now in the inner core, which has a radius of 1,220 kilometers, 758 miles. Unlike the outer core, the inner core is solid. Despite its staggering temperature, the immense pressure prevents it from melting. What happens under such extreme conditions? The inner core is primarily composed of an iron-nickel alloy, with lighter elements such as silicon, sulfur, carbon, oxygen, and possibly hydrogen. It stays solid due to the immense pressure. If we could see it, the core would appear to shine bright white. This inner core serves as the heart of the planet's massive magnetic field generator, shielding us from harmful solar radiation and allowing life to thrive without the need for underground bunkers. What about our samples at this depth? Water likely remains in its supercritical fluid state, but there's a chance it could transform into hot plasma. Plasma is an exotic state of matter typically found in stars, thermonuclear reactors, or within the body of a lightning bolt. Iron, on the other hand, would find itself in its native element, but under extreme conditions. Surrounding it would be the Earth's iron-nickel core, heated up to a whopping 6,000 degrees Celsius. That's 10,830 Fahrenheit, which is hotter than the surface of the Sun. Add to that the overwhelming pressure and the iron would transition from its molten state back into solid metal glowing almost white. And what about hydrogen? One might wonder if hydrogen would finally acquire metallic properties at the Earth's core. Unfortunately, no, it's more likely to remain in a supercritical phase. For metallic properties, it would need a pressure of at least 4 million atmospheres, preferably 5. Where can such conditions be found if Earth's core has a pressure lower than 4 million atmospheres? Obviously, on other planets of the solar system. That's our next destination. When it comes to pressure, the gas giants Jupiter and Saturn, along with the ice giants Uranus and Neptune, are particularly worth exploring. These planets have very different compositions. Jupiter and Saturn are primarily composed of about 3/4 hydrogen and 1/4 helium. Let's take a brief journey to Jupiter. After passing through the gaseous and gas-liquid layers of its atmosphere, we reach a point about 0.8 radii from the planet's center, where we encounter a vast ocean of liquid hydrogen and helium. The pressure at this surface is about 0.69 million atmospheres. And this ocean is unimaginably deep. Let's descend another 8,000 kilometers, 4,970 miles. Here the pressure reaches 2 million atmospheres. The liquid hydrogen exists in a highly exotic state, but hasn't yet to begin transitioning into metallic hydrogen. And what about helium? Since the ocean contains not only hydrogen but also helium, it's worth noting that helium stays in its standard liquid form. Interestingly, helium is denser than liquid hydrogen, which is why the two liquids start to separate. As we go deeper, the pressure continues to rise. At 20,000 kilometers, 12,500 miles beneath the surface, the pressure hits 4 million atmospheres, and hydrogen begins transitioning into a metallic phase. By the time we reach a depth of 25,000 kilometers, that's 15,500 miles, metallic hydrogen stabilizes. This form of hydrogen conducts electricity but remains in a liquid state. Under gravity's influence, heavier helium droplets start to sink through the viscous metallic hydrogen towards the planet's core. This process releases some heat, and what's the result? We observe a growing layer of helium around Jupiter's core, accompanied by thermal energy radiating into space. Today it is assumed that this heat is one of the main reasons for Jupiter's energy oddities. What oddities, you might ask? The fact is that Jupiter radiates much more heat into space than it receives from the Sun. By the way, a similar phenomenon occurs with Saturn. This means that the planets have their own internal sources of heat. Helium rain in the layer of liquid metallic hydrogen appears to be such a source. The same happens on Saturn and Neptune. But something even more interesting occurs on Neptune. Should we fly there? Neptune's composition is different. Its atmosphere and interior are rich in water, methane and ammonia. These stable substances behave predictably until the pressure exceeds 1 million atmospheres. At this point, methane breaks down into carbon and pure water. What happens to the carbon under such pressures and high temperatures? You guessed it. Neptune's atmosphere provides perfect conditions for diamond formation. Diamonds form directly in the atmosphere and under the influence of gravity and other physical processes rain down onto the planet's surface, creating a spectacular phenomenon known as diamond rain. Now imagine this, millions of tons of diamonds slowly descending through the dense murky darkness of an enormous planet.